Okay, you guys want to say hi to her or something?
Hello. Hi, Ashley.
There we go. Okay. What's that?
Show up for school for once.
Oh, man.
Chris, show up on time for once. You're right.
He was here before. Oh, you mean for physics? Yeah. Okay. So the probability of obtaining tails when a biased coin is tossed is 0.57. We've tossed this coin 10 times. It says find the probability of obtaining at least 4 tails. So here's what is actually, I tell you what, you're probably going to get a mark for writing this, that capital X is distributed binomially with 10 trials and probability of success being 0.47. What did I say? Whoa, and I wrote 5.7. Weird. Anyway, oh, I know why. Because we're working on 4. So here's what the questions ask you to do. It's asked you to find the probability that X is, now if I say at least 4, what am I saying? 4 or more. So greater than or equal to 4. However, binomial distributions on our calculator can't go to the right, they can only go left. So 1 minus, what goes in these parentheses? Less than or equal to what? 3. We want to be careful because 4 or more was what we were looking for. So if it's not 4 or more, it's clearly less than 4. Well, since there's nothing between 3 and 4, you got to go with just less than or equal to 3. Cool? All right. And then from there, it's a calculator question. What you're not going to do is you're not going to write binom CDF or anything like that on your paper. But that's what it is. We're doing CDF, cumulative, because it's adding up the probability of 0, 1, 2, and 3. And then it's subtracting those 4 different things from the number 1. You know that time I said my graphing calculator was at home? I was wrong. He was in my backpack. I just didn't know it. I just found it last period. So we go 1 minus second vars. And we're doing binomial CDF. Number of trials is 10. Probability of success, 0.57. And the X value we're hunting for is 3. See, I've already typed the 1 minus part. So it's going to give me the answer I'm looking for. 0.919. Well, it is because it's a biased coin. And you're flipping it 10 times. So the probability that it lands on what you wanted it to land on at least 3 times should be really, really high. So that's going to be... It's an unfair game. 0.919. There we go. This next question is really interesting. It's not so much a binomial distribution style question. It's more like a, I don't know, I want to say common sense. It's not really common sense, but just like thinking your way through it. It's only worth 3 marks, so it's not like it's a lot of work. It's just the thought process. It says the probability of obtaining tails when a biased coin is tossed is 0.57, so we repeat that statement. The coin is tossed 10 times, gotcha. Find the probability of getting the 4th tail on the 10th toss. So what is that telling us? Right, so we have found 3 on first 9 trials. 4th on, whoa.
What was that? What is that?
Okay. Realize that this is an and statement. So we know we found 3 tails in our first 9 trials, and we got a tail, the 4th one, on that 10th trial. So how do we show that there were 3, exactly 3, found in the first 9? Right. So we're actually trying to find the probability of X equaling 3 in the first 9 trials. So when we go to our second vars, down to normal, binom PDF, because we're looking for exactly 3, our trials isn't 10. Our trials is 9. probability of success, 0.57. And now we're looking for it to be exactly 3. So that was the probability that we found 3 of them in the first 9. And you see, it's not a very large number, and that should make sense. Because it being a biased coin, it wants to land on tails, and you're saying 6 out of 9 times it landed on the unlikely side, is what you're saying. So that's why that number is so low, so that should make sense. But when we say and we all know, I hope, that individual coin tosses are independent, right? So we have to take this probability, and what do we have to do when we say the 4th one happened on the 10th trial? Multiply by 0.57. So it's insanely unlikely, 0.0561. 0.0561. If you wrote 0.056, you didn't get that mark. 3 sig figs. Leading zeros do not count as sig figs.
I just did. Could you write that as a 0.6 like 5.61%?
Yes, you could, yeah, because that is still 3 sig figs if you wrote it as a percent. I wouldn't though, just because it gives you one more chance to do something wrong. Oops, I moved the decimal too many times or not enough times. I would just stick with decimals. Because I think it's just less work. So yeah, that's a tricky question, and not very many people get it right. Yeah, it's just, and that's the thing is, when the first time I did it, I had to think my way through it. Like I think I spent more time thinking about the question than doing the question, because I was like, okay, what are they saying if I know I got 3 in the first 9 trials? And then it's like eventually something went click, and I was like, oh, I got it. There we are. So let's move on to normal distributions, and unfortunately I do think that normal distributions are much more difficult than binomial distributions. So these are just extra practice questions. They're just generic questions I have that I've pulled from the question bank. You can see that they're not my former test questions. They're just former IB test questions in general. And you don't think you can fit it on here? That's not bad. I mean, it's like 2 marks, 2 marks, 3. We should be able to fit it. Because remember, a lot of this is going to be done on the calculator. Where's that 5-mark question? Yeah. Yeah, it's still, most of it gets done on the calculator. We'll be okay. The weights in grams of oranges grown in an orchard are normally distributed with mean of 297. And what do we know? It's known that 79% of the oranges weigh more than 289 grams. 9.5% of the oranges weigh more than 30. Find the probability that it weighs between 289 and 310. Yikes. Well, what I would do, because I'm not very good at seeing these things in my head, I draw a bell curve for basically everything. What were you going to say?
I was going to say, never mind. Because couldn't we do one trial just below 310 and then have a limit at 289? Or make a limit at 289? I remember.
Well, we have to be between these two numbers, though. So this is our minimum and this is our maximum.
I don't remember what.
Well, here's the thing. We were actually told that only 79% of them weigh more than 289. Yeah. So I'm going to draw a bell curve because it helps me out a lot. Yeah, but it's a huge one behind it. And so we got ourselves a bell curve. And what do we know? The mean is 297. I'm going to cheat and use different colors. We don't know the standard deviation. Normally, these things would be written like this. X is distributed normally with mean, and then there would be a sigma. I'm assuming we're going to have to solve for sigma in a moment because we don't know it. Standard deviation. It is known that 79% of the oranges weigh more than 289. Okay, so I've got a 289, which is to the left of 297. And what was the next number? 310. That's over here somewhere. Picture's not drawn to scale. So if we know that that area is 79% or 0.79, and we know that this over here is 0.095, what do we need to do? So if we subtract, it's going to give us everything to the left of 310, right? So let's just write it out like this. The probability that x is less than 310 is just 1 minus 0.095. I don't want to get this decimal wrong, Chris, so I'm going to use my calculator. I said I don't want to get this decimal wrong, so I'm going to use my calculator. 0.905. Is that what you guys meant?
Yeah.
Oh, I thought you were doing it harder than that. I was just following your guys' lead. Okay, that's how I would have done it. I just thought that you guys meant find the other side. So next time, I guess don't let me assume what you mean. So then what we should have done was, well, when you guys said subtract, because I had just written this, I thought you meant like, okay, let's find the rest. I thought that's what you meant.
Don't be ridiculous.
Well, I mean, you never know what people are thinking.
We love you.
So what do we say? It's going to be 0.79 minus 0.095. 0.695. Much better. Okay. Now, it says the weights of the orange have a standard deviation sigma. Great. We're going to need to find the standardized value for 289. When they say the standardized value, what does it mean? Yeah, it's looking for a z-score. That's what that means. It's looking for the z-score is the number of standard deviations.
Oh, I hate these.
Well, you see, it's only worth 2 marks. So it's not like it's a system of equations or anything like that.
I have to know z-scores again.
Well, there's a formula in the reference sheet for a z-scores.
What are z-scores like?
A z-score is a number of standard deviations above or below your mean. So if you get a z-score of negative 0.8, that means you are 0.8 standard deviations below the mean. That's what a z-score is. And our standardized normal variables, check it out, it's right here. It's the last formula in the reference sheet. Oh, do I need to go up so you can see it better?
Yeah.
There you go. So it's just the last formula. Here's what we know. We know x, it's going to be, is it 289? Is that the one we're working with? 289. We know the mean, it's 297. We need the standard deviation. So how are we going to find standard deviation?
Well, that's the next question. So you set a standard deviation of 1 being 0.
Oh, if that is the next question, then wouldn't find the standardized value for 289? What do they mean by that?
It's a good question, Mr. McCutcheon.
So not a z-score, it just wants to know. Oh, okay. Gotcha. Gotcha. When we do normal CDF, we never use normal PDF. When we do normal CDF, what this thing is giving to us is a probability, an area under the curve. We know some areas under the curve, don't we?
Yes.
So what we're going to do is we're going to use known areas to get back the number of standard deviations that they are away from mean. So if it's not, it doesn't do normal CDF to get the areas, we're taking the areas to get back to the x value that get it to us. That's going to be inverse normal. So it's using the backwards information. So we go to inverse normal. And you'll notice that
So do we just plug in any of the number? We don't know this.
we don't need, so what this does is it assumes that you're trying to find a number of standard deviations. And then in the next question, like we just said, we're going to use this formula. We'll put that answer we get for this one right there, and that's how we're going to solve for sigma. So in order to figure out your standard deviation, the number of standard deviations there are from mean, you can just use inverse normal. Inverse normal only goes left unless you have a fancier, newer calculator. It only goes left. So which area do we want to use? You want to use a left area. So we could use the one that I found a little bit ago, because I thought that's what you guys asked me to do. And we could say that there is 0.905 to the left of this number, but that would be a waste of our time since we're trying to find this, 289. So what is to the left of 289? 0.21, because that's 1 minus 0.79. So 0.21, and we leave 0 and 1 because that's standard normal, and this will tell us that we are that many standard deviations. Wow. The example that I gave you actually said, I said negative 0.8, didn't I? Okay, well, it's on video. I'm pretty sure I just made that up a minute ago, and it was actually the answer for this one. So negative 0.806 is what this thing wanted you to write.
So could you explain again how you found the number of standard deviations without finding?
Because so normal CDF takes an X value and turns it into an area. So inverse normal takes an area and turns it back into, quote unquote, an X value. But what it's giving you is the X value on the standard normal curve, where the standard deviation is 1 and the mean is 0.
So it's telling you how many standard deviations.
So inverse normal will give you back the number of standard deviations that you are away from mean.
So negative 0.806 would also be the z-score.
That is the z-score. And that's how we do the next part. That's how we solve for sigma. Because the formula requires you to know sigma to get a z-score by hand. So we now know this number, we know this number, and we know that number. That would allow us to just do some basic algebra to solve for sigma. So our z-score, negative 0.806, is our known value of 289 minus our known average of 297, but we don't know sigma. So perform the old switcheroo. This number and this sigma just switch places. Let us find our standard deviation. 289 minus 297 is divided by that number. Standard deviation of 9.92. A sigma, excuse me. No, I said it right. Standard deviation. Yeah. No. Oh, did you do second answer?
Yeah, that's what I did too.
Did it not come out to 9.92 when you did that?
I got 9.92.
Oh, okay.
I got 9.92, but it rounds up. Did I round 9.8 because but that's only if you type in 0.8.
Oh, you typed in 0.806? That's fine. You typed in a 3 sig fig number. That's fine. That's always going to be acceptable. Remember, their answer is a range of answers. It says anything that falls from here to here counts.
It just increases my chances of guessing randomly.
Yeah, it does increase your chances of guessing randomly. So the gross... What? Yeah, right. The grocer at a local grocery store will buy the oranges whose weights exceed the 35th percentile. To the nearest gram, find the minimum weight of an orange that the grocer will buy. All right. So what does the 35th percentile represent? It means it's only better than 35% of the material. It's like when you take your SAT or ACT or whatever, you can't ever score the 100th percentile. You can only get 99th percentile. That means you're better than 99%. You can't be better than yourself. It doesn't make any sense, and that's why 100 percentile doesn't work. So we're talking about a normal distribution again.
What if I change the bell curve?
Change the bell curve. So we're doing this. This is just for visual purposes. we know that we're trying to find out above the 35th percentile. That means 35% of the material is landing here, and 35% as an area is 0.35. Make sense? Okay. So now we're going to use area to return this value right here. Okay. Reverse integral. Stop that. That's confusing. We're using an area to find stuff, okay? Now, check it out. We go to second vars, and we're going to go to normal. Inverse normal gives us back an x value, so we're going to go to inverse normal. We now know sigma and mu. We found those, right? The area clearly is wrong, but our mean is 297. Our mean down. Oh, it won't let me go down until I fill in this area. So 0.35, because that is to the left of wherever we need to be. Sigma is 297, and we just found that to be about 9.92.
Okay, so we're putting.
So if I had left it 0.3501,
Yeah.
it would have just told me how many standard deviations I was below the mean. That's what that would have told me. But I need to know the actual weight of the... Is it an orange? Yeah, I need to know the actual weight of the oranges. So this is going to return an x value, so to speak, on this span. And we know it's going to be bigger than 289 because that was 0.21. But we know it's less than 297 because that's 0.5. Here we go. 293, to, what did it say, to the nearest gram? 293 grams. Negative weight? It says minimum weight, 293 Gs. The orchard packs oranges in boxes of 36. Find the probability that the grocer buys more than half the oranges.
So he'll buy oranges at X. So I don't understand what this question is asking.
Okay, so you know that our grocer is only going to buy an orange if it weighs 293 or more.
Yes.
Okay, all right. There's a box of 36 oranges now, but that doesn't mean that they are all going to make the cut. So what we want to know is what's the probability that more than half weighs this or more? What's it sound like? It's binomial. It's a binomial distribution because an orange either makes the cut or does not. It's either heavy enough or isn't. What's the probability it's heavy enough? 0.65, because that's the opposite of this. So this area is your 0.65s, and that is now the probability of success. Now I can't use capital X, so I'm going to have to use a different variable. So we're going to do this. We're going to say that capital Y is distributed binomially. How many trials are there? 36. With a probability of success of 0.65. And it says more than half. So what we're actually trying to find is that the probability is Y is greater than 18. Hold on. So if it says more than half, right? But that means, since it's binomial, I can't buy 18 and a half oranges. So the first number that's greater than 18 is 19. So Y is greater than or equal to 19. Oh, shucks, shoot, darn. Binomial distribution stuff only goes left on our calculator. Yours can do anything? Yeah, well, you know what? I'm not rich and I don't have a nice calculator like you. I know it's the same one. I can see it. I never updated my operating system. I don't know how. Yeah, you bought yours sooner. If it's a more recent purchase, it always has the newest software on it.
So you just sell that one and buy it.
No, I'm kind of attached to this one. I guess I just need to update the operating system.
Yeah, just plug it into.
Yeah, I just need to plug it in. I have the cord. You guys borrow it all the time.
It's not there.
1 minus second vars. Now, again, this is binomial, so we're going to go all the way down to binom CDF because it's a span of numbers. 36 trials, probability of success is 0.65. We want 18 because it's or less. Alrighty. Hey, look at that. There's a 0.954 chance that we're going to buy more than half of these oranges. That makes sense because it was a 65% chance that each orange was good. Come on, pin.
So since it was like half,
More than half.
but like since it was a ratio of 36, if it changed the number, like so if it was 4 box of 40, would the number still be the same?
So if we were always so if there was 40 trials and we were still trying to get more than half, I think it would stay the same.
Yeah.
Want to find out? Okay. 1 minus, and I have to say I think because I honestly probability and statistics. So 40 trials, and we want this thing to say 20. So we said more than half again.
Yeah.
I think it's going to give us the same result. It didn't. How about that? Well, that makes sense. You think about it. Each orange is a 0.65. So if you say, what's the probability that I picked 5 of them? 0.65 times 0.65, times 0.65. So it makes sense that it was a little bit, but it's bigger though. That's interesting. Interesting. Cool.
Oh, it's 36.
Yeah, I mean, it's close, but it is different.
Yeah, because it has like a higher chance.
Neat. The grocer selects 2 boxes. Remember, a box has 36 trials in it. Our grocer selects 2 boxes at random. Find the probability that the grocer buys more than half the oranges in each box. What do you think you're supposed to do? You just square the number, yeah. Because this is the probability that a randomly selected box will have you buy more than half. So if it says you pick 2 boxes, what's the probability that you accept more than half from both? It's this and then this again. So it's just going to be that number squared. So I'm just going to hit squared and hit equals 0.929. There it is. Fun question.
I have a question.
Yeah, what's up?
So if you use the value that you got in your calculator, but
Mm-hmm.
you wrote that squared, it's not the same thing.
Oh, they're not going to care about that. No, so this is a 3 sig fig answer, and it doesn't matter that you wrote the 3 sig fig answer because if it never stops, how could they punish you for truncating here, you know? So yeah, no, it's okay if you use the calculator value and get a more accurate answer.
But it only gets a box.
How many was it? I don't know if I missed what you said.
I'm sorry?
You just take the
So it
exact
gets a
same
box of 36. You like,
answer that you got from the binom CDF and you just square it twice.
No, I just squared it.
only gonna buy
I mean, like you just
Mhm.
square it, it's a different answer. It's 0.91.
Mine's not.
What's the problem?
It's because we used the wrong size.
That's your wrong. That's the wrong one. You used the 40. You used your 100 tested.
Oh, dang. My B, guys. I'm sorry. That's my mistake. Here, clear. Oh, whoops. Yeah, I didn't mean to clear it. Whatever. What was it?
I got.
I'm just going to square 0.954 squared.
Yeah, you get
0.91. Okay, sorry. This was my I blame Michael. It's his fault. Yeah, I used your experimental
Oh, my
question, yeah. Oh, I'm so stupid. Look at this. I scribbled out the correct thing.
That's your fault.
That's my fault. That's on me. Thank you. All done, you said?
yes.
Gotcha.
Depending on the results, I might take it.
There is no third chance. That's because that was the retake.
You want that still plugged in?
Yeah, we'll leave it charged. Thanks. Well, they don't keep a charge over the weekend, so. Okay. Using the wrong number here is Michael's fault. Scribbling out the correct stuff was my fault. Moving on. Don't talk about it. I haven't seen that movie yet.
Oh, it's a
You know what?
It's not a movie?
You know what's the best movie of all time? Space Odyssey? Morbius. Oh, I love that. I love Morbius. The best movie.
I don't understand. Is it a movie?
Yeah, it's
apparently not good.
Oh.
It's the Marvel like vampire one.
Oh. Yeah, my wife wanted to see that. I don't know why. It looks like trash.
I started seeing those memes. That's like the best movie ever, and then I quickly realized that's not the case. Yeah.
Yeah, no.
That's like 60% off.
Eh.
There's things that are worse than that.
Okay.
Yeah, 16 out of 60.
The mass of apples in grams is normally distributed with mean unknown. Uh-oh. Okay. If they tell you that the mean is unknown, guarantee you're going to have to find it soon. Hopefully it's not one of those system of equations ones. However, that being worth 5 marks tells me it's probably one of those systems of equations ones. We'll get there. We'll get there. Following table shows the probabilities of masses. Write down the value of K. Well, what do we know about these 3 things? They add up to 1. So there's 0.98. There's 0.99. K is 0.01. There. Show that the mean is... Oh, no. Okay, cool. Show that the mean is 106. How? It's what? Between what?
It's in the middle of the data. So that's up to 1.
Right. So because it's normally distributed, yeah, we know it's symmetric. And because these 2 numbers match, we know that our mean is directly in the middle of this. So what do? You do 119 minus 93 divided by 2. That doesn't make any sense. Sorry. I was meant to add them. I'm trying to find the average. 93 plus 119 divided by 2. There we go. And that'll be 106. The average of those 2 numbers. Yeah, oh, you found the distance between them, divided by 2, and then added it to 93 or subtracted from 19. Yeah. It works. This is faster. But yeah, that's when I started doing it. I was like, yeah, that works perfectly. Because you did what I was about to do. You figure out how far away the 2 numbers are. And what are they? It's like 26 apart. So you just add 13 to that. Yeah, works perfectly. Yep. So let's find the probability that m is less than 95. Well, remember, x is distributed normally with mean of 106 and standard deviation of crud. How in the world are we going to be able to find... What's that? We can use inverse normal to find a z-score. There we go. So the reason why this is worth 5 marks is because we can use inverse normal, and I would say we just go directly to this because we already know what's to the left of this number. Use inverse normal to find out how many standard deviations this is from our mean, and we'll go from there because we could then use our z-score formula to solve for sigma. And then once we know all of that stuff, we can handle that. So that's why it's worth 5 marks. So I'm not going to write inverse normal on the paper. We're just going to go directly to our calculator. Please don't write inverse normal and stuff like that on your tests or your IB exam. Remember what inverse normal does. It gives you back a number of standard deviations. Since we don't know sigma, we need to use standard normal with 0 and 1. So stick to that. The area that we're going to use is to the left of 0.01, so really, really small. And it tells us that that is 2.33 standard deviations below our mean. That is a z-score. So we can go directly to our z-score formula. That is down here. We know x. We know mean. We know z. We don't know sigma. So negative 2.33 equals, that x was 93. And our mean was 106. And that's how we're going to solve for sigma. switch these two again. It tells us that sigma is, so 93 minus 106 is divided by that number, because we switched the sigma and the negative 2.33 to give us 5.59 standard deviation. Good with that? Okay.
What would we, in order to make it 3 sig figs, what would we round it to?
To make what's 3 sig figs? That is 3 sig figs. That is 3 sig figs.
I'm sorry, I thought it said 5.595.
Oh, okay.
I just had way out.
No worry. My pen, do you see that?
Yeah.
It's refusing to write in that little blue spot.
It's being sassy.
There. Now that we know everything we need, we could actually use normal CDF to find the area below this value. So we are now attempting to find the probability that capital X is less, at capital M. This drives me nuts. Look at this. Capital X here, but a capital M here, and then they used freaking capital M. That bothers me. If you were going to use, they're going to use X here, it should have been lowercase x, not uppercase. Uppercase implies that you called the distribution X. Whatever. We'll just use their variable that they wrote. So now that we know mean, and we know standard deviation, and we know the X value that we're looking for, we can find the area to the left of it. So second vars, normal CDF. We never use normal PDF. I don't know what it does. I'm sorry. No, I don't know what it means, honestly. It's some other stat class that I didn't take. Our lower bound, yeah, that's an exceedingly small number. Our upper bound, though, is 95. So this is nice. Normal CDF goes left or right. It doesn't go center on my calculator. Do anybody else's? Oh, wait, yeah, it does. Center could be lower and upper. Yeah, so this one's really nice. It does both. Yes, Dylan, what's up? What's that? I didn't. The calculator defaulted to it. If you have a number there, you could put like negative 1,000 or something like that. So mine default.
It calculates the function.
What's that?
It calculates the distribution function. The probability distribution function.
Really? That's what that does?
It does.
Neat.
I always.
It actually gives you the probability distribution function. That's cool. Let's see. Our mean we said was 106, and our standard deviation we just found 5.59. Let's figure out what's to the left of 95.
94.
0.0245.
No, it's not.
Leading zeros. I can't count.
Yeah, leading zeros don't count.
I went one more.
Okay. I'm not going to lie, the first time I did 2C, took me quite a while. Because what did I do? Okay, let's do it again. Let's do it like this.
Oh, you didn't look at the information above it.
I didn't look at the information above 2C like it wasn't important. Very gifted / intelligent, IB-ish kind of thing for you guys to do is to skip over stuff that looks like it's not important, but it is. So when in doubt, reread, okay? So yeah, that information given to you before 2C is kind of necessary for you to do 2C. Apples are packed in a bag of 10. Uh-oh, I'm automatically smelling binomial distribution. Why else would they have told me how many there are? Now, I don't know when I'm going to need binomial distribution, but the moment I know how many apples I'm dealing with, we're thinking, okay, they're going to say, what's the probability I buy 6 or more or some bull like that, okay? So apples are in a bag of 10. Apples with a mass less than 95 are small. So the probability that an apple is small is that. Find the probability that a bag of apples selected at random contains at most one small apple. Okay. Well, we can't use X, we can't use M, so I'll say Y. Y is distributed normally. Binomially is what I meant to say.
To change the variable, do you lose all marks?
I don't know if you what.
Because that's bad method
in the sense that you're using the same.
Yeah, if you use the same letter, I'm not. I don't know. Sometimes you get marks for this, sometimes you don't. So if it's one of the questions where it wasn't part of the method mark, I don't think it would count against you. But if it was part of the method mark,
I think you'd get screwed over if it's required.
yeah, no, even if it's implied.
Oh, okay.
Yeah, so I would just be really careful with your letters.
Okay.
We know that there are 10 trials, and even though it sucks, our probability of success, quote unquote, is that it's a small apple. So 0.0245. Find the probability that a bag of apples selected at random contains at most. So at most implies what? Yep. Less than or equal to. Less than or equal to 1. Second vars, binom CDF, because it's going to add these things. There were 10 trials. Our probability of a small apple, which is actually success, is 0.0245, and you're hoping it's 1 or less. So a very good chance. And the reason why is because a small apple should have been extremely rare. Only 2% of our apples are small. That makes sense that 1 or less of them is small. So 0.976. A crate contains 50 bags of apples. Okay, so what is this? This is the probability that a bag of apples is 1 or less small apples. There are now 50 bags of these apples. So these 50 bags of 10 apples each. Uh-oh. That was my phone telling me Chappie just shut down. Oh, class is about to get out too? Okay. It says find the expected number of bags in this crate that contain at most 1 small apple. So what are we going to do? Expected number. How do we find expected number? NP. Yeah, it's just NP. So it's 50 times this number that we just got, 0.976. So it's times 50. 48.8. No, expected value is allowed to be small. I mean, it's allowed to be not part of the set. Find the probability that at least 48 bags satisfy. Remember, this is the probability that we're satisfied, 0.976. So when you say at least, you mean that number or less. So the probability that y is less than or equal to, oh, it's not even y anymore, is it? Y was a single bag. Now we have to have a whole nother variable. Let's use, we can't use z? That's z-scores? Let's use k, sure, why not?
Wait, K is a variable.
Man, you guys are killing me.
Just W.
W, yeah. W is distributed binomially. Do we know how many trials? 50 trials? And the probability of success is 0.976 W for win, because we're the best. So what is the probability that W is less than or equal to 48? Second vars, binom, CDF, 50 trials, probability of success 0.976. Wait, the bell is ringing. 48 or less. Give it to me now. There we go. 0.338. Boom.